Hey guys, this is Carrie, and this is the answer key video for homework number 7. Alright, so let f of x equal a times b to the x power plus c, where a, b, and c are constants. In addition to this in class, we added the extra restriction that a is greater than 0. We're going to keep that. Which of the following results in exponential decay? So let's see. If you remember in class today, we noticed that if b is greater than 1, what that would mean is we've got something like this, I don't know, like 1.30 to the x power plus c, and this would represent a 30% increase because it's 100% plus 30%. A 30% increase, that does not sound like decay. This would be exponential growth. So if b is greater than 0, that's exponential growth. For exponential decay, what you want to be thinking about is you want to be thinking about the opposite situation. Let's say you have a 30% decrease. Then what kind of number are we going to end up with for b in our formula? So 30% decrease, that would be decay, and that would look something like this. So 0.70, that would be an example of a b value that would result in decay. This value is not less than 0, so that would be not a correct answer choice. But this value kind of subscribes to both 2 and 4. So how do we pick between 2 and 4? So the way you can pick between 2 and 4 is this. The most you can decrease by would be 100% decrease, right? You can't lose more than what you started with. So if you had 100% decrease, that would mean a times 100% decrease would mean from the 100% you start with, you lose 100%. So your b value would be 0 to the x power plus c. So it looks like what you get here when you, if you have exponential decay, is you've got a range of possible decreases, 30% or 100%. And whether if you reduce by 30%, you end up with a b value between 0 and 1. But if you reduce by 100%, that would mean you lose everything, and so b would be 0. It's impossible to get a negative number for b because you can't take 100% what you have and lose 102%. So because you can't lose more than what you had, it looks like b values are restricted to being between 0 and 1. That's the correct answer for exponential decay. That was a little bit more wordy than I wanted it to be, but the most you can lose 100%, so you can't have a b value less than 0. All right, let f of x equal this. So what is the equation of the horizontal asymptote? So we've been playing around with equations like this, exponential equations, for a while. And one thing that we observed was that the horizontal asymptote is always this final value in the formula. So our horizontal asymptote is y equals -5. So if we were to draw a little sketch of our function here, y equals -5. 1, 2, 3, 4, 5. I think this is the first time we've had a negative value for the y-asymptote, but I wanted you to see that before maybe seeing it on a Regents or test. What's the y-intercept of this function? So what we observed is the y-intercept will always be this value plus this value. So for b, this is a, for b, the y-intercept would be 3 plus -5. It's -2. I think this is also the first time we're ever seeing a negative value for the y-intercept. And then lastly, we've got, is this an example of exponential growth or decay? And what we said before is if this value, the b value, is between 0 and 1, meaning that we've lost something from 100%, this would be exponential decay. It's a value less than 1. So what we've got is we've got our classic exponential curve, exponential decay, so we start very high up and we decay, oops, I don't want to drag it, we decay down to the asymptote through the y-intercept. So this must be our function here. Next up, the student is graphing the function f of x equals log base 3 of x minus 2. Write how you would input this into your calculator. So we know that to input it into our calculator, we have to do log of the expression divided by the base that we were doing, log of the base. So that's why 3 is on the bottom when we plug it into the calculator. After inputting the function, the calculator generates the table below. Based on the table below, what is the equation of the vertical asymptote of the function? So the vertical asymptote is a barrier that divides the error region where the graph doesn't exist from the region where the graph does exist. that barrier is at x equals 1. So at x equals 1, we have a horizontal, that's not right. At x equals 1, we have a horizontal asymptote. Let's draw it in red. So to the left of this value, 0 and 1, we have errors. So the graph never reaches this region. However, to the right of this, we actually have values. So we have 2, 0, 3, 1, 4, 1.585, 5, 2. Great. So you've got this section here. So now the important thing is we don't want to make the mistake that a lot of students are making in class. We have this vertical asymptote, and so our function should asymptotically approach this, getting closer and closer forever. Now we've got our function f of x equals log base 3 of x minus 2, using the data from the table that you could generate from your calculator. For part 4, you invest $25,000 in an account that earns 9% yearly interest. If interest is compounded quarterly, write an equation for the value of the interest, for the value of the investment after 2 years. So if it's compounded quarterly, that means it's going to be 4 times per year, each quarter. And so of course, you're not going to earn that full 9% each quarter. So the way you compute the percent for quarterly would be take the full year percent, and we don't get it all at once, we get it in 4 chunks, so we're going to divide it by 4. That gives us 2.25%. So our quarterly percent growth is 2.25%. Next up, we need to start to write our equation. So our equation is going to be a of t equals 25,000. And now we don't just use this percent here, it's growing by this percent each quarter. So we have to take 100%, add it to how much it's growing by, 2.25%. That results in 102.25%. And so when we put this in our formula, it'll be moving the decimal twice, 1.0225. And then rather than raise it to the t power, because it's being compounded 4 times per year, if we waited 1 year, we should compound it 4 times. If we waited 2 years, we would compound it 8 times. If we waited 3 years, we'd compound it 12 times, 4 times each year. So to do that properly with our exponent here, we're going to multiply by this 4 times each year, so we get 4 times the number of years that we have. So this is our proper expression. If the expression is compounded monthly, then things are going to look very similar. So we end up with needing to get the monthly percent. So find the percent. Monthly would mean 12 times per year. So then you get 12%, no, not 12%, excuse me. It's 9% for the whole year, divided into 12 chunks. That is 0.75% per month. Then we take, it's growing by that, so we take 100%. Each month we grow by 0.75%. Combining these together will give us 170.5%. That's not right. Sorry about that. I got distracted. That's going to be 100.75%. So this is our proper monthly percent growth. And so we get A of t is equal to $25,000 times 1 point, moving the decimal twice, 0.0075. And if it's compounding 12 times per year monthly, then it'll be to the 12t power. Next up for C, it says to calculate the value of the investment after 5 years using each of the formulas above. So I'm going to flip over to Desmos to do that. So we've got 2 different functions here. I'll call them f of x. Oh, wow, I don't know how to use Desmos on this yet. So f of x is equal to 25,000 times 1.0225 to the 4x power. So let's see. That was for part A, the quarterly one, right? Because it's the 4th power. So it looks like we're plugging in 5 years. So I'll just use function notation to do that. To plug in 5 years, we do f of 5. And that results in 39012.73. right, now in contrast, if we plug it into our monthly formula, let's see how things change. So for our monthly formula, we need to change the percentage. So this is going to be a different number here. It's 1.0075, I believe. And then the power will be the 12x because it's happening 12 times. Let's see if we got that right. Whoa. Let's see if we got that right. Yep, that looks right. All right, so the value that we get is $39,142.03. 39,142. Oops. $42. So what you can see is this clearly makes a big difference. When you compound it monthly, you get an extra $130. It's not exact. I'm avoiding the change. I hope you did it with the cents, the change, but about an extra $130. So it makes a big difference whether you compound things quarterly or monthly. Monthly, that's not monthly, monthly. And I think you'll find that the more frequently you compound things, because you get extra compounding, it's actually better. All right, for problem number 5, you're going to have to figure this one out on your own. There's a nice little problem here, problem B, that uses some logs. I hope I didn't give too much away, logarithms, but you should be able to figure it out. All right, bye.